of the cybersecurity group and affiliated to UCL's System Security Research Lab. His research interests are at the intersection of system security and machine learning, with a particular emphasis at the intersection of system security and machine learning. Sorry, because I have just one moment, the echo I've solved. I was saying that his research interests are at the intersection of system security and machine learning, with a particular emphasis on settings in which attackers adapt quickly to new defenses. In particular, non-stationarity adaptive attackers. And previously, he obtained his PhD in computer science at the University of Modena in Italy. And he visited the University of Maryland, College Park, USA. And he was a postdoctoral researcher at Royal Holloway University of London. So I'm pleased to give the stage to Fabio, that will deliver his talk entitled Trends and Challenges in Machine Learning-based Malware Detection.
Thank you very much, Amro, for the introduction. I occasionally get echo with this setup, so, well, not myself. I mean, if you hear any echo, feel free to just interrupt me. I am excited to be here. Thanks for inviting me. Today, I decided to do something a bit different than the usual presentation. I tried to collate and organize a cohesive story based on my some of my recent papers about the trends and challenges in machine learning malware detection. After a brief introduction about myself, well, I mean, thanks, Amro, also for the background. I want to acknowledge my team and where I work. And I will present, I want to touch briefly on static and dynamic analysis and pros and cons of both approaches, and then move towards machine learning-based malware detection. But the focus of this talk will be about, in a sense, challenges in solving malware detection tasks through machine learning, and I will talk about especially concept drift and adversarial malware. So just want to mention that my specific department in King's College London is in Bush House, which is an historical building at the heart of London, the so-called heart of London, close to Covent Garden. This is a view of the front gate of the building, and a view from the on the right-hand side, on the bottom right. You see also a view from the, this is a picture I took myself from the top of the, it's like on the level over my office. We have a very nice balcony with a very nice view of London. So if you ever stop by London for work or for recreation, just if you want to catch up, drop me an email, and I'll be happy to try and arrange something. And this, I'm just also showing over here that since in London space is usually an issue, they recently managed at King's to start a plan to make pedestrian the area in front of Bush House. So there would be a sort of a bit of a campus feeling, and it's called the Strand campus and the Strand like neighborhood. Before going into the talk, I want to just introduce a bit my research vision, so also to contextualize a bit better where I'm coming from and where I'm headed to. I have the main objective to design practical security solutions that try to explore the intersection of AI and machine learning to learn behavioral models that can recognize novel attacks and threats, generate decisions that can really assist human security analysts, and to take into consideration also attackers with realistic capabilities, which in the context of malware means the ability to modify real-world programs instead of just relying on the feature space. So in a sense, you could summarize this as is practical, explainable, and robust machine learning for system security possible? And I would like just to take a moment to acknowledge all my closest collaborator in my team, my PhD students, Theo, Mohamed, Jacopo, and Mark. And most of the work I'm going to present today is also being significantly contributed by our kind of alumni, Fergus, who was actually as first supervisor at Lorenzo at UCL, whom I'm working closely with at the System Security Research Lab. And I also like to collaborate a lot. So I have a lot of research collaborators. You will find in the, if you look at the author lists in the paper that I report today, you will find most of these people. And this presentation and this research could not be possible with all of them. So I want to start by offering a bit of context also for people that maybe are familiar with machine learning and security of machine learning, but not necessarily with malware detection. For convenience, I will assume maybe an Android, or if you want, an iOS case study in which we have applications, which are just self-contained applications, but you can imagine this can be portable executables in Windows. And the first thing that we want to do is perform some static and dynamic analysis on them, because at the end of the day, they're kind of a bubble of bytes. And we want to extract some more high-level information to know more about their behaviors. And in static analysis, basically, we evaluate the computer software without executing it. In a sense, we could take an Android APK. It could be source code, a binary executable, and we can try to represent the behavior of the program through abstractions such as control flow graphs and abstract syntax trees. Whereas in dynamic analysis, it's kind of an orthogonal approach in which we evaluate actual executions of programs to infer properties and behavior. So dynamic analysis is mainly conducted through the same principles of debugging, like when you insert breakpoints, you monitor and track the values of variables and states of the system. And typically for dynamic analysis, you have to kind of sandbox the system. You use sandboxing as in like isolating the execution of an application, because if it is malicious, you want to contain a malicious behavior. For example, you do not want the ransomware to infect your own system. There are many pros and cons of static and dynamic analysis, which kind of complement them. For example, the main limitation of static analysis is that it is very weak to obfuscation. Imagine like if an entire Java class is encrypted and just dynamically unencrypted and loaded in runtime. If you just analyze without execution, unless you recover the decryption or like unpacking routine, you're not able to see anything. And maybe the major limitation of dynamic analysis, on the other hand, is about the fact that you may execute an application, but you may not trigger any malicious behavior for real. So in a sense, this could be also summarized in the sense that in static analysis, we could say that we have an over-approximations of the behaviors of a program, which means that there may be parts of the code that are never executed. We have a good coverage in static analysis because we can explore the whole application, if we are talking about source code, the whole source code. But maybe some paths are just very, very rare, or maybe are never really executed in practice. So we may lose time, and attackers may also try to just introduce junk sections to add distractions, right? In dynamic analysis, we have instead another approximations of the behaviors. Think about like a Facebook app or a social network app in general. You may execute some of it, but it's very hard to, especially out in an automated way, trigger all the possible behaviors or code paths. So I just want to emphasize that at the heart of machine learning-based malware detection, there will be static and dynamic analysis. So the so-called like static features extracted through static analysis and dynamic features from dynamic analysis. Inherently, sorry, not pun intended, but static features inherit the limitations of static analysis, and dynamic features inherit the limitations of dynamic analysis, but also the strengths. So in general, using a combination of the two is would be generally lead to a more robust classifier, although of course it may become a bit more complex or time-consuming to extract and manage. But in relation to this topic, I would have a question for you, but since there are many of you, I'm just going to give you a second and think about, is static analysis faster than dynamic analysis in your opinion? And the answer, as in most of like engineering and computer science, is that it depends on the precision that you want to achieve. And I just want to specify this as well, because I myself had this misconception in the past that static analysis was just faster because I could, for example, count the API calls. And in practice, if you count just the API call frequencies, even the driving Android malware classifier can analyze an entire application in a few seconds, even on a research prototype that is not implemented in C. And but you have some forms of static analysis, such as taint analysis, data flow analysis, information flows that can be very, very slow and time consuming, taking hours or days for individual apps. At the same time, while a dynamic analysis environment may be a bit more maybe difficult to set up in the first place, but imagining that you both have a static analysis platform in place and the dynamic analysis platform in place, to just execute 10 seconds per app, it may be a lot faster than just a heavier static analysis and more precise static analysis. At the same time, of course, if you start doing a long execution time and you take into account also restoring the state of the dynamic analysis system and performing advanced stimulation to possibly trigger malicious behavior or multiple runs, then of course it becomes more slow. So far, I mean, I didn't really talk yet about detection, right? So we just did static and dynamic analysis to extract some information about the program behaviors. Traditionally, what will be done and what is still being done also for, if you think about antivirus system or network intrusion detection systems, is to use signatures. And if the signature is found, we classify the application as malware. If the signature is not found, we classify it as goodware. Of course, here I say signature, which can be a sequence of bytes. You may have more complex rules. For example, Yara is the language to specify rules based on regular expression. So you can define quite complex rules, but still it's mostly a manual effort in a sense. And in terms of possible outcomes, I just wanted to emphasize that the concept of like ground truth and true positives, false positives, and so on does come even before machine learning. It's just in traditional detection system that you would consider that. So in terms of possible outcomes, if the system predicts an application as malware, you may have either true positive or a false positive, if in reality it was malware or goodware. Vice versa, you may have a false negative or true negative, depending on whether the prediction of being a goodware was correct or not. What we want to achieve is to maximize the true positives and true negatives and minimize the false negatives and false positives. In practice, there is always a sort of trade-off, and I just want to anticipate that typically antivirus companies tend to reduce false positives. And this is because they imagine installing a new antivirus, and every application you install, it triggers it as malware, tells you it's malware when it's clearly not. After 12 notifications, you probably uninstall the antivirus software. So that's the reason for why they typically tend to prefer low false positives. But of course, a false negative would mean that you did miss a malware. So signature-based detection does not scale well. It's error-prone and time-consuming, and attackers have just so much more time than defenders to invest in malware development. So that's why there was an attention in moving towards using machine learning models to automatically learn classification rules to distinguish between goodware and malware by learning from the data. So giving them examples of applications preferably labeled. And you could say that machine learning models tend to generate a probability as an outcome. So you could say that if the probability is greater or equal than 0.5, it's a malware, or if it's lower than 0.5, it's a goodware. You could read it also as 50%. This is also one of the possible thresholds. You can imagine that if you want to be really, really sure about the malware that you classify, you may want to increase this threshold in a sense, so that maybe if the probability of being a malware is over 90%, you would classify it as malware. So you may be very well, I mean, you don't need me to say that machine learning has been extremely successful in production in many tasks. If you think about your phone, whether Android or iOS, a lot of like facial recognition, speech recognition, and machine translation is just happening on the phone, right? However, in security, it has been it has been explored and deployed in companies, but still not to the same extent of success of the other tasks, probably. Or at least it seems to be more challenging and to take more considerations to consider more things, to take more things into account. So why is that? And I guess that the thing, at least the answer that I gave myself, also discussing with my collaborators, is that the specific situation is that our specific condition is that the security domain is adversarial by nature. So if we develop a new detection system, immediately attackers will try to evade. So here on the right-hand side, it's just a rough distribution of goodware and malware. And in general, if attackers want to evade detection, then one of the ways in which they could do that is like make their malware look more like goodware based on our abstraction. So in general, this causes dataset shifts that do not happen naturally, but they happen because adversaries constantly keep trying to evade any detection system. And if you think about it, in practice, also facial recognition systems don't work at all if you consider a very an adversary with a high incentive. So I guess that in general, machine learning originally was not thought with adversaries in mind. So that's why now we are trying to understand how to adapt machine learning for security tasks in the context of this talk for malware detection. And I want to just give you a quick overview of the phases of, well, it's not machine learning for security. Well, you could say machine learning for security, but in this case, it can be for malware analysis. I like just to present it with Pokemons. We have Pikachus on the left and Charmanders on the right. So these are our training data. We do some data collection at first. We have some labeled application because in machine learning, we want to learn from the data. I know that there are machine learning algorithms that work with unlabeled data, but for simplicity, we will ignore that. And after you collected some data and some labels, the second thing you would do is like some pre-processing and feature engineering. To some extent, we could say eye size and height here. Apologies because it's not perfectly semantically relevant for the example, because of course the eye size of the Pikachus and Charmanders is not, well, it is different, but among the same Charmander is not necessarily so much different. Oh, sorry. And well, what you want to do, you want anyway to extract numerical information from this Pokemon? Well, we can say that the Pikachus on the left are goodware represented in yellow, and the Charmander on the right are malware represented in red. So what the machine learning does is that you select a model, you perform the training, and will identify, according to some assumptions of the model, a separation boundary that distinguishes between benign and malicious applications. At test time, we have a new application appearing on the right, depending on the side of the decision boundary. In this case, it will be classified as a Charmander, so as a malicious app. So typically, the traditional machine learning tasks, in a sense, to some extent, end here. And the peculiar phase in security, in general, when you consider security in a machine learning task, but especially malware detection, is that you need to consider that malware evolves over time because attackers change their strategies. And there are, in general, adversaries that could take advantage specifically of the fact that you're using a machine learning model to try to detect them. And I want to start by talking about concept drift in malware detection. I want to just give an intuition first. Let's add another Pokemon to the set. Like we have a Squirtle, upwards, and these sort of puddles. I think it's called puddles, like the anyway, these areas of more intense color in the center can represent the decision functions. So we have a 3-class problem, and the test time in terms of drift, we may have 3 possible situations. We may have either an evolution of an existing class, which could or could not be classified correctly, and an entirely new unseen class that in traditional supervised classification with a fixed number of classes would be misclassified regardless. So this is something that we need to take into account. And initially we started evaluating we started thinking in general about the most simple thing, like evaluating papers in a time-aware fashion, right? Because of course, if you train on the past, and in general, you should train up to a certain point and then simulate a deployment, so test on what's coming next. So this helped us identify kind of one misconception that we had from the machine learning literature, where k-fold cross-validation was very commonly used. So let's consider a timeline here with malware above the timeline, goodware in blue below the timeline. And towards the end, let's say last year, a new type of malware came out, which in machine learning terms, it will mean that it comes from a different distribution. So now I will just split this data set into 2, sort of an extreme k-fold, in a sense, a 2-fold or a random split. So we have training on the left, testing on the right. But if you notice, the new malware that just came out last year is now in the training set. So it will be much easier for the classifier to distinguish the sample, the recent new variant present in the test set. So in a sense, violation of this temporal consistency use future knowledge in training. So this is not per se incorrect, and it was found independently by Kevin Alex and Brad Miller and others, at least in the security context and the malware context. But in a sense, it's kind of just estimating as the best that your classifier can do. It's like you're simulating performance in absence of concept drift because you're using future knowledge in the training set. You cannot get better than that. And in machine learning, it was traditionally done because, for example, in text or in images, you don't have too much of a drift, right? The second point that we actually identified, still related to time, was about the dataset composition. Here on the left-hand side, we have very futuristic goodware from 2021. Actually, I should update it to 2022. And on the right, we have very old, obsolete malware, right? And let's say that in 2020, a new API comes out and becomes a new standard for a very common thing, actually related maybe to creation of sockets. So what happens is that a machine learning classifier learns from the data. It's not intelligent per se. So what the classifier will learn is that this specific API is perfect for distinguishing between good and malware, but it's completely unrelated to maliciousness. It's just a spurious correlation. So we defined a framework called Tesseract, published at Usenix 2019, where it's just a framework that enforces 3 experimental constraints to avoid experimental bias. I already talked to you about the first 2. The third one is just about, and we refer to it as spatial bias. The third one is just about using a realistic percentage of malware in the test class, basically. And I want to show you also what is the concrete impact on detection models, because we also wanted to quantify what was the actual impact, because intuitively preserving the temporal consistency makes sense. But you may also argue that maybe the impact is not too much. So we trained, we took actually 3 approaches from the literature. Here I will show you one first. And we trained on 2014, 100 apps from 2014. And on the x-axis, you see testing periods in months. So it's like 2 years. And it is spanning 2015 and 2016. On the y-axis, for simplicity, I just report the F1 score, which is a performance metric between 0 and 1, and 1 is the best. So the original paper reported several results, but the best tenfold performance obtained was about 99%. The first thing that we can do, since I mentioned to you that the tenfold could estimate the performance in absence of drift, but you have to use the realistic percentage of malware that you expect to see in the wild for your domain. Even already enforcing this, reduce the performance a little bit. But when we enforce all the temporal constraints and evaluate the performance month by month, then we have a huge performance decay. And we wanted to capture this in one number, because otherwise we would end up also with papers with endless plots, and it would be very difficult to read. So we define it similar to the AUC or the ORC. We define the area under time, for example, by specifying also metric and periods. For example, the AUT in terms of F1 score over 24 months is 32%. Okay, now we have the tools to compare different approaches in a time-aware fashion without spatiotemporal bias. So you see here that, so here are the results for 3 approaches. And the fun thing for you to note is that approach number 3 was the weakest on paper, if you look at the black line, out of the 3 of them. But in practice, it's the most robust one against time decay. Approach number 2, on the other hand, is very, very good for the first few months. So in case this was just an extreme scenario in which there was no retraining involved. So assuming that you may retrain, you may also consider using approach number 2. But that actually brings me to the point, like, so what about this framework? Well, it allows to do realistic evaluations to simulate more realistic settings of what would happen in deployment. It allows practitioner to choose best solutions and researcher to evaluate new solutions, but also it enables you to evaluate not only F1 score anymore. It's not only about performance. You may consider a labeling cost for retraining strategies, also in terms of manpower, and potentially quarantine cost for rejecting samples. Out of the possible solutions, such as incremental retraining and active learning for adapting to drift, we have explored especially classification with rejection approaches, which basically reject the low confidence objects that are low confidence. So if we are unsure about a certain classification, we reject it, right? And I want to talk to you a bit about that now. So the intuition is that, well, actually, I was not in the original authors of Transcend, but we have a follow-up on this. This was done by the System Security Lab System Security Research Lab, led by Lorenzo in 2017. And the intuition of this framework is that when new examples come in, we have an underlying classifier, and Transcend was introducing a conformal evaluator theory that generated confidence value with statistical support from the training data, which was fed to Transcend. That was an optimization approach to identify an optimal confidence threshold. And then based on whether the confidence threshold was met or not, the decision would be accepted or rejected. Just I'm putting an asterisk there because I said confidence, but we have in practice Transcend extracts, the framework extracts credibility and confidence for each value, which is defined statistically for each training object. So sorry, for each object, for each test object, test sample, and training point as well. I'm not going to go into the detail because I wanted to give you more of an overview, but the major limitations of Transcend was that, well, from an experimental perspective, there was possibly sampling a spatial bias in how the experiments were defined. And the role of confidence, because I just told you that we have both credibility and confidence for each point, the role of confidence was unknown. And the thresholding was also suboptimal because it was kind of an exhaustive search and it took a lot of time. But maybe the major limitation was that the computational demand was just too high. I do not remember the number exactly, but it takes a few weeks to run experiments on a simple data set. So what we did for our upcoming paper at SMP 2022 is think how to improve on the transductive conformal evaluator. So the original conformal evaluator was called transductive or TCE for transductive conformal evaluator. And to generate statistical support, you need p-values for all the training points so that you can compare the test points against them. And in the diagram represented here, that means to get the p-value for the points, for the point in dark blue, you have to leave it out and retrain the underlying classifier all the remaining points in light blue, and then repeat until you have p-values for each point. And this induces enormous overhead. So our first attempt at reducing overhead was was the approximate TCE, where we leave out points in batches and do the retraining on the other points. However, it relies on the assumption that the decision boundary doesn't move that much between points in a batch. And this assumption is not very reliable and has the potential to undermine the statistical soundness of the technique. So it's not an entirely satisfying solution. So the inductive conformal evaluator, ICE, aims to reduce the computational overhead of the TCE by operating on a training calibration split where we only generate p-values for a subset of the training points. Now we are able to get the soundness back, but it has the problem of being informationally inefficient. We're only using a small portion of the data for statistical support when we want to use it all. So the final approach is cross-conformal evaluator, or CCE, inspired by k-fold cross-validation in an attempt to reduce both the computational and informational inefficiencies of TCE and ICE. You split the training set into folds, end up with one conformal evaluator for each fold, which perform a majority vote to assess the prediction. So here are some results. I mean, I went quite quickly over that. It is quite complicated and it requires some thinking. So I advise you to read the paper if you're interested. But at the end of the day, these are just 3 alternative ways to produce a statistical value that gives support from the training data whether a certain prediction is reliable or not. You can see it as a sort of a confidence score, right, on which a thresholding is applied. And here is a comparison between approximate TCE, ICE, and CCE. And in general, what I want to highlight is that we computed also the overhead in terms of CPU hours. You see it in the small rectangle, as well as the AUT. So these are the same plots that you have seen in Tesseract. And the long story short is that if your priority is speed, you should go for ICE, otherwise CCE for high confidence. But just as a note, despite the fact that CCE has a lot of more GPU hours, every fault can be just parallelized. So this was, I just showed you one way in which also to tackle concept drift that we explored. But after working on Tesseract, we also realized that it was not only about spatiotemporal bias. So people started coming to us and asking, but is Tesseract the only thing I need, or is there something else? You didn't consider this aspect. So we started really thinking, and in a collaboration with TU Braunschweig and myself and the System Security Research Lab, we recently published a paper, actually set to appear at Using Security 2022, in which we identified the common pitfalls. And the goal of this work was really to try to identify the common pitfalls and how we can avoid them to try to improve the state of empirical research in machine learning for security. So we ended up identifying 10 common pitfalls and derived some recommendations on how to mitigate them. Here, the pitfalls are presented in order of which stage the typical machine learning pipeline they're likely to appear in. So we have first data collection and labeling, then system design and learning, then performance evaluation, and then the final deployment stage. And an important remark is that it's not really it was not our intention, never, also with Tesseract, to just point the finger at anyone or place the blame on anyone. We did these same mistakes in the past, or we did not consider some of these pitfalls in the past. So it's more of, and the point is that the presence of a pitfall does not automatically invalidate the value of a piece of work. We really wanted this to be a reflective exercise that we can do as a community, and our own work is included in these studies. And the objective is to try and improve the state of the experimentation moving forward. So now that we've got, I mean, I didn't give you an exact definition because I wanted to give you an overview, but I want to just show you a prevalence study that we did just to show the impact. So we consider 20 papers from top conferences in security covering many topics. And we devised a set of possible values, like whether a pitfall can be present, partially present, not present, or unclear. And we assigned 2 reviewers to each paper. And if there was any dispute, a third reviewer was involved. But in case of uncertainty, the original authors are given the benefit of the doubt. And out of this survey, it comes out that so all the part that is more towards red or warm colors indicates that one of the pitfalls was present. So every paper in this study also had 3 pitfalls. So this was something that was generally prevalent, although the awareness was, of course, different depending on the pitfall. And yeah, that's, I mean, in the paper, I forgot to add maybe a reference, but in addition to just having a description of the pitfalls, the prevalence studies and recommendations, we also have 4 case studies, experimental case studies from 4 papers from different domains in which we tried to show the impact of some of these pitfalls. In a way, to some extent, similar to Tesseract, but of course it went beyond time-aware evaluations. So if this was not enough in terms of challenges that are currently faced in malware detection literature, I want to conclude by talking about the MLaware adversaries. And but before I proceed, I want also to mention that these challenges, from one perspective, are a problem, but from the other, are an opportunity for coming up with new and creative ideas. I think it's a very exciting field to be in at the moment. So in traditional adversarial machine learning, I mean, you may have seen to the ad nauseum a panda, and the image of a panda in which some perturbation is added and the adversarial image is generated. These are usually called feature space attacks, and the objective is to solve an optimization function where you want to minimize the pixel perturbation and the loss of the target class. And typically, to represent the pixel perturbation, you have the norm of the noise vector. But what happens when you move to like the malware domain? Okay, so we have an original application Z, a malware X. Sorry, the original application Z, which is a malware. And we want to add some perturbations or noise to classify if it's a good word as an adversarial app. So, I mean, in a sense, this is formulated as for images, but what does it actually mean to add perturbation to code? And well, if we look at the optimization function from before, the first thing is that we do not really care anymore about the norm of the vector to some extent, because whereas in images there is sort of a direct correspondence between pixels and features, so that the perturbation vector results in a perceptual perturbation as well, although of course it's debated of whether that is a good measure indeed. But here, I mean, if we add 100 more API calls, it's not going to be like alert an analyst per se or reverse engineer per se. I mean, there's something else about it, right? Of course, I think that is different is that if an app starts waiting 1 terabyte, an Android app, that becomes very, very suspicious. Well, potentially even unusable, but you may have different things to take into consideration, right? And for example, is it realistic or plausible for a human analyst? Does it crash when you execute it? Does it preserve the actual malicious functionality? But more specifically, I mean, here I'm reporting and discussing the malware detection setting, but in practice, there are a variety of domains in which this can be a problem. And a lot of papers were being proposed. So our paper was not the first one in this field per se of proposing a problem space, this called problem space attack, right? What was missing was a sort of unified framework with general constraints to take into consideration when defining such attacks, sort of a new type of threat model, an extension of feature space attack threat model. And I want to emphasize, actually, I forgot to mention that the very main challenge here, which does not allow to just run the same attacks as in images, for example, is the inverse feature mapping problem. Even if we identify a solution, well, we can identify a solution mathematically to know which malware features to change, but in practice, we may be just unable to, I mean, once we identify the adversarial feature vector, how do we get back to the adversarial application? Especially, how do we get back to the exact same application but transformed? I mean, it's not a one-to-one correspondence like we have in images. So this is the major issue that creates challenges in conducting problem space attacks. And we identified 4 major problem space constraints that need to be taken into account. We also extended the general formalization of the problem, where you see on the left-hand side was the more traditional feature space attacks. On the right-hand side is our extended formalization of the problem space attacks. If you read the problem space constraints, I'm sure that it's kind of intuitive what they mean in terms of defining the available transformations. What semantics do you want to preserve with the transformation, plausibility of the application if it's inspected manually, and robustness to preprocessing methods, such as dead code elimination, which was one of the things that was mostly overlooked by prior work, such as adding bytes at the end of the malware. Even compilers remove that code. So if it's not going to end up in the feature, your attack is just ineffective in practice. Another thing I want to highlight is that we also evidence that now we do not only have feature-driven search strategies, such as gradient-based or projected gradient descent and this type of attacks. We also have problem-driven strategies, such as through genetic algorithms on Monte Carlo simulations, in which we try to randomly modify the application and try to see whether the decision function is going without actually having an idea of the underlying gradient or behavior of the model. And we can also have hybrid methods. So this allowed also to, so this framework also now allowed to systematize and identify weaknesses on existing methods, and allows also to understand better how to improve on the state of the art. And we instantiated it on a lot of tasks, even the traditional ones that were solved with just feature space attacks, such as the speech recognition or the facial recognition tasks. And I just want to, well, in terms of results, I do not want to go in detail on this figure because I want to leave time for questions. But what we managed to do is, in the Android setting, we also defined a new problem space attack that was more exhaustive than the previous one proposed in the literature. And we identified the previous limitation thanks to our framework. And we did low and high confidence attack against both SVM and SecSVM, which is a more secure version of SVM proposed actually by the team at University of Cagliari. And we managed to actually evade with real-world modified malware created in less than 2 minutes, even the SecSVM, which was reasoning on, I mean, in practice, as SecSVM works, it increases the number of features that the attacker needs to modify. But what we showed is that in practice, in the malware context, the number of features is not very indicative of the effort of creating realistic code. And to conclude, I guess that the security and malware detection domain is highly non-stationary and often imbalanced. There is an arms race, a constant arms race, because the domain is adversarial by nature. And in my research, I really try to move towards more practical solutions and more realistic deployment evaluation. So both with Tesseract and with the do's and don'ts paper, identifying major pitfalls and recommendations for improvement. And in my research, we also have designed classification with rejection-based methods to solve distribution shifts, to adapt classifiers to distribution shifts that naturally happen in malware. And but rejection is only one of the possible approaches. You can also consider, for example, active learning, online learning, or completely changing the paradigm. And adversarial attacks in the malware domain are feasible. And we introduce a problem space reformulation that can help you and assist you in tackling this problem. And I just wanted to mention also that the coding data sets for, I think, all of the research I mentioned here, but in general for all our prototypes, even the ones that I didn't have time to cover today, are available for available. So we have already, you just have to fill a collection form, and we'll be happy to share with you. And we are already have more than 120 organizations that requested access, including some honorable mentions here. But if you're interested in trying this out, just let me know. Actually, if you go on the, I think that most of the request forms are on the projects page on the S2Lab website, but the specific papers contain the instructions. So thank you very much. I guess this concludes my presentation.
Thank you for the talk. We have a question from Luca, I see. So Luca.
Hello, can you hear me?
Yes, thank you.
Okay, so first of all, thank you for the talk. It was very, very interesting to see this very giant overview of all of these topics revolving around machine learning and security. That was really, really appreciated. I want to ask a question on the malware side, like not totally unexpected. When you are removing the distance constraint from the optimization algorithm, I want to ask, because I think I didn't get why you removed that from the optimization problem, and you didn't even put it inside a hard constraint.
You mean here, right? Like when I crossed this.
Yes. Yeah. So I think I lost. Why?
So yeah, no. The intuition is that this constraint was originally developed in images to limit the. So in a sense, this was. If you just did an adversarial attack on images, especially unconstrained, or maybe you wanted to reach just a certain confidence, you could introduce just too much noise in the image, so you could see that the image was something was wrong with the image, right?
Mm-hmm.
What I was arguing here is that, well, in a sense, I guess this was a bit more succinct to give an intuition. It's not necessarily wrong to add it. What I wanted to say is that so what I meant here is that let's say that you have a classifier that has API calls as features.
Mm-hmm.
And you have an image classifier that has is a 10 by 10 image classifier.
Mm-hmm.
If you modify 100 pixel is very bad for the image domain, but if you add 100 API calls, I mean, especially from the perspective of a human, of plausibility from a human perspective, it may not change much. Of course, it depends on how you do it. So what I wanted to argue is that it's not anymore just an LP norm-based constraint. There are more constraints to take into account. Then one open challenge left from the work was also that, of course, even in our attack, we follow kind of a greedy approach and partially empirical approach to identify the possible constraints on the data. And so what is missing is maybe a linking which you could define analytically also problem space constraints, right? So in a sense, it's what would be the LP norm, but for malware, right? If it's trying to capture that type of perturbation.
Because I think, because I have a comment on that. I think that in general, when you create adversarial examples, you don't use just LP norms. You have a distance function, when you want to you minimize an objective. In the case of malware, I mean, it could also be the difference in bytes, a number of bytes that you have injected inside. Let's say Windows malware, it's the same for Android applications. So it's still a cost that you have to pay. Also because so my comment was, it depends maybe on the goal that you want to achieve. So if you want to show the brittleness of your classifier and just say that I use just 3 bytes and I just evade detection, or if I don't care about it, I think now that I have I think I got the reason why you removed it. So thank you.
Yeah, no, I mean, I also get your comment, and if I remember correctly, you have worked more also with Windows malware, right? So for another project here, I just mentioned Android, but in practice in Windows, I have to mention that, especially when modifying Windows malware, because assuming that they're binaries and we don't have the source code, it's relatively easy to break stuff, and much more easier to break than Android. And even in that project, we also tried to ask ourselves whether we should limit, in general, the number of modifications that we would do. in general, more than in terms of normal features, I would probably think about it as maybe you want to maybe limit the transformation chain that you create or something, right? But I understand also your point that to show the brittleness of your classifier, if you just add 3 bytes or a certain string, yes, then probably the classifier is just very, very broken.
Yeah, so I think I lost few parts of the answer. I think I'll just ask later because I have some connection issues on my side. So
okay.
I'll ask you later.
I'd be happy to follow up. Yes.
Yeah, no, but no, my comment was that I think that maybe like you can just reintroduce this, distance inside the optimization either as a soft constraint, like with the regularizers, or also like as a hard constraint. Also, because if you inject like 200 APIs, maybe even if they are not executed, maybe if I open let's say that I am a reverse engineer, so I open up with Ghidra or with IDA, and I see that there are tons of APIs that are included. Maybe this is getting a bit more suspicious. So that's why I'm asking, because I think it depends on the target that you have in mind.
Yeah, no, I see. What we did is actually introduce constraints on the, I may get a bit confused on the specific experiment of that paper because we have been working on follow-ups as well. But we, instead of like constraining the number of things, we were more like, do we fit in the distribution of the goodware in terms of number of API calls, cyclomatic complexity, and maybe even size of the application, presence of multimedia. And we also ensured for possibility that we kind of added real code from other applications like Transplanted. So we didn't just add we would not just add 100 API as is. We would try to add context with it. So, but let's say that removing this was more provocative and for intuition. I agree with you that there should be some sort of distant function. What I wanted to say is also that we should not reason only about features, because about limiting too much the feature, like restricting defenses by using very small feature perturbations, or we should consider situations in which the attacker has more freedom in features and maybe less freedom in modifying the software.
Thank you. Thank you.
Let's see if we have other question. Some raised hand. Seems no. We have a question in chat. And that is, I think we can say that concept drift is the changing of malware's feature while it follows the same goals. So other than try to identify samples to retrain the model, do you think it is possible to use explainability, the feature which are critical in decision of the model, to generate new samples, whether on problem or feature space, to use them for retraining the malware?
Okay, I'm not sure I understood 100% the question, but so from the first part of the, well, there is a comment at the beginning in which like, yes, in a sense, concept drift can be seen as a natural, there is anyway this belief that concept drift can be seen as a natural form of adversarial in a sense, or actually adversarial can be seen as a worst case concept drift. In a sense, the attacker may not be aware that you're using a machine learning classifier, so they may not be using gradient attacks and so on. But what may happen is that, indirectly by changing the malwares to evade the detection system, of course, they start kind of removing the features. If you're suggesting to use, so the question was about whether explanations may be used to retrain the model to make it more robust. In that case, I think potentially, well, I mean, first of all, it depends also a little bit on what you mean on explanation, because you may have local explanations and global explanations. I mean, it can be a bit of a vague term, but if you're talking about like understanding how the feature space is changing, yes, that can be a promising direction to explore in general. Trying to understand, I mean, in a sense, you want to, so let's say that with the Tesseract framework, at least you can evaluate in-house how robust is your classifier to concept drift. If it's very weak, you may need to change either the classifier or the feature engineering because something may not be working. So even before thinking about retraining strategies, the first step that you can take is even just evaluating a classifier per se.
Okay, we have time for a last question because we are running out of time. So we have seen a raised hand from Steve Cuttle. So if you can unmute yourself and make the question live. Then we will have the other question, but first we will stop the live on Zoom, okay? Please, Stephen.
Hi, so I was just wondering about the conformal prediction.
You're very, sorry, your microphone volume is very, very low for me.
Sorry, I will just speak louder. I was wondering about the conformal prediction stuff. If you did any analysis to see where it failed, did it fail on like old families that had been moving, or did it fail on new malware families that weren't in the training data?
So we did a bit of inspection on the false negatives and false positives. So there is something in the latest version of the paper. If I remember correctly, because we are doing something more related also to families, as you mentioned, like whether it was new malware and this kind of things. At the time, we did not have a data set with the families, so we did not reason in general about maybe appearance of new malware per se. So, but we did try in different domains. So we tried it also on Windows malware with the Ember classifier, and on PDFs with HIDOST. So if you actually look at you have to look at the latest version of the paper. It's probably not still in the proceedings, but we updated the latest version on archive, which is the camera ready. And it has much more experiments because the paper had we added a lot of experiments over time. So.
Okay, so I think we should stop with the question because we are running out of time. At least we will continue after we close the Zoom live. So I leave the stage to Maura.
Yes, I just want to thank Fabio for the amazing talk and also the most followed talk because we have many viewers today. And thank you all for joining us today. So
thank you all for coming.
I stopped the live streaming.